These slides review a few different concepts that we didn't have time to talk about during our class meeting. It covers measurement system concepts in general, but also I'll talk a little bit about data acquisition systems in a very general way, just so that you can distinguish these types of systems rather from the approach that we are now taking in this course, which is more based on the use of the Arduino microcontroller platform. And in so doing, I'll also talk a little bit about A to D conversion and converters. Again, not trying to go into too much detail, but I think it can be useful in trying to understand really what an Arduino does that's different, say, from maybe some of the commercial data acquisition systems that you might run across later in research projects, internships, or in your careers. And I believe that in talking about the Arduino, we might also hit on some of the specifications. Okay, so here, this first little diagram here, just a very generalized idea, if you like, of a measurement system. And, you know, we like to use sort of this system bubble to represent a physical system in general. A measurement system is then something that we set up that has, right, all of this different hardware, has the sensors. And so I've broken it down here into this diagram is really sort of a key piece of this, right? I have some other definitions here that are used. You know, these terms are common in what you might call measurement science. A measurand is a referent, where a referent is some system attribute that's of interest or relevant. Like, you know, for the simple pendulum system, we're studying the angle, right, the velocity. These are also state variables, and then a referent actually might be specifically a measurand is actually a referent that's actually measurable. So those are some terms that are used in measurement science. You know, maybe not so important here, but if you might run across them in other contexts. What we're interested in the information that we're trying to measure using sensors and so on is that there's information that's important in them. And so again, that's another way to think about this in a very general way. You can also think about having two different systems that you focus on. One is the sensor system, and then the other might be breaking it apart, that you might have some signal conditioning. And signal conditioning has a lot of different components in it. And then what comes out of the signal conditioning is a signal of some form, right, that then goes into some device that can measure it, right, record it. Maybe it goes to a controller. And so we'll talk about, so by the way, the difference here is if you're learning modeling with the bond graph approach, right, the difference that we like to use is that a half arrow is a power-based flow, right, or it's a power flow, whereas if you just see where you see a full arrow, that's just signal. Signal just means, you know, that there's no power, and in fact, this representation actually is two signals. You might have one going in one direction, one going in the other direction. You learn that in bond graphs. Again, this is just a general figure. Now we'll get a little bit more specific. We talk about now signals, and in the electrical domain, we like to code those signals in different ways. People design different kinds of sensors, and you might then design the sensor so it encodes whatever it is that you're measuring in different ways. And so be cognizant of the fact that you might buy sensors that have those signals that are analog in form, which means that the magnitude varies, you know, in some kind of continuous manner. You might actually code it up also in terms of time. So like an encoder, which measures, say, shaft position or velocity, is actually giving you that information in terms of time-based information, right? So you're looking at the time between different pulses, right? So the actual amplitude isn't as important as the difference between the pulses in time. Okay, so you need to interrogate time in those cases. And then there might be also some digital signals where you actually get integer values from some sensors, and so there's some processing that goes on before you actually measure that. Okay, so just be aware of the fact that you could get some sensors that are coded in different ways. We're going to be talking mostly about analog sensors in this course. I've always liked this little diagram here. It just kind of shows this idea. I'm going to blow up this little figure. It shows how, if you think of the physical domain and you being able to then code information in all of these other different domains, right? So you could go into the analog domain, you could go into the time domain or the digital domain. Above this line here, as you can see, it's non-electrical, whereas below it is electrical. And so you could have all these little pie sections here show that you could code information in different ways. And I've always found this a very interesting kind of way to think about this. I'm going to show you a little example of how that could work in the case of they say a thermistor digital thermometer measurement system. These thermistors might be in a Wheatstone bridge here. So this circuit here, this Wheatstone bridge, which you might be familiar with from a circuits class, is allowing you to measure changes in the resistance of these thermistors down here and converting that into voltage, right? We call that a signal conditioning process. And then there's actually different steps here. That voltage is converted into frequency, and then frequency is using a gating circuit is counted so that a counter then displays, say, some information about temperature. And so this little diagram that we looked at before, as you can see down here, shows you how those information transformations occur from temperature to resistance and a physical electrical quantity. And then when it makes this jump down here, right, it goes into voltage and then frequency and then counts and so on, and then finally to a number, right? So again, kind of an interesting way. This is from a book by Malmstat on electronic measurement for scientists. It's a very comprehensive reference on measurements, and so I've always found that to be a very interesting way to think about that. So the measurement system concepts that we're interested in this course, right, is mostly through the use of hardware and software. Now focusing down in this course, 144L, we're adopting Arduino, open source hardware, and also Python to accomplish these purposes, right? In past offerings, we've used National Instruments hardware and software using LabVIEW. So I have some discussion in these slides about data acquisition systems from National Instruments as a comparison to Arduino. And again, the Arduino hardware, provides this manner of connecting to the physical world to collect signals, to process them, and so on. And then the software that's both in Arduino as well as on the desktops that use in Python is used to do some of this processing. So our measurement systems that we're building in this course are going to be composed of those components. And so I'm going to talk a little bit about all these little pieces that go towards that. Again, to give you more context in terms of what a general data acquisition system does, again, to distinguish it from the base Arduino system, overall, when a data acquisition system is built, and you can see down here, maybe just to go to a different color just to highlight it, is the data acquisition system accomplishes a lot in this piece. Okay, we have the sensor and the signal conditioning part up here, but then overall, right, what your data acquisition system does is it converts all of that into some digital form so that you can do some data reduction. And down here, this little diagram of a signal flow scheme shows you all the pieces that might occur there. You might have a way to handle all these signals, to put them into an A to D converter. And then one of the things that's key about data acquisition systems is that they might have a way to also buffer the data and to store it. And the Arduino itself doesn't have that. We have to send the data immediately off, and that's why we're grabbing that with a desktop computer, using Python. We're going to be doing that. And then, you could then communicate with the data acquisition system, or to display, to store, or there could be an external computer, right? So actually, the storage is here. The buffer could hold the data. For example, you might give the data acquisition system a command that would say, take so many data points, and it would have enough, storage and the onboard systems to do that. Again, with the Arduino, we can't do that. And so I'm just showing some examples here of how these can be realized in different ways, showing you different desktop communication. There's serial communications, the old RS-232 version, which is a serial port. There's also some other types of interfaces, GPIV. You might, so like in these, you can see these are actual devices, a digital multimeter that communicates via an interface, or some other kind of instrument where actually all the measurements being done out here, and the computer is just asking. To some extent, the Arduino is not unlike this, except some of these devices, putting way too many check marks on there, aren't I? Is maybe designed to have some special data acquisition functionality on board also, right? So it can store and so on. There's also rack systems that you could find, such as this one here, where they have some signal conditioning on board. A lot of times these externally are used also because you're trying to maybe measure very low level signals. There could be a lot of noise. Once you get a board inside a computer, then it's subject sometimes to a lot of noise from that environment as well. So if you're doing very sensitive measurements, sometimes it's better to buy the special hardware that can measure low level signals, say, do processing before you get it into the computer. Nowadays, it's become very common to use the USB interface, and the NI MyDAC is one educational platform that we've used for that. This has a little data acquisition system on here, as well as a digital multimeter, and this can be used for experiments and so on. And of course, there's wireless communications from computers to different types of hardware. And this shows like a 4-channel A to D data acquisition system. So you can have 4 different channels that you can collect data from, right, analog signals from. The Arduino, again, is a microcontroller, so it wasn't designed for data acquisition, but if you look around online and so on, you'll see a lot of people trying to do that, either loading the data onto SD shields, or using Python, as we're going to do, to grab the data from the serial port, and that way you can collect data and do kind of what a data acquisition system does. You can process it and so on, and then of course do other things with it. So I'll leave it up to you to really review the Arduino itself, what it does, but it does have, one of the things that makes it unique is it's got the microcontroller, right, this ATMega 328, and that microcontroller itself has additional hardware on it. The communication support is key, right, the USB. In a lot of cases, that's where we get our power, but of course you can bring power in through this barrel jack. There's power management circuitry on board, and there's circuitry, the circuitry for doing that. There's also a 16 megahertz crystal that allows that microprocessor to run a little bit higher speeds. And what else? Oh, and then all the connections, right? So you have all of these different headers that allow you to connect to sensors and so on, and you can get those directly into the microcontroller. In the case here, the microcontroller itself is what has the A to D converter on board, right? So it's all part of that chip. And so as opposed to having a data acquisition system that has an A to D converter inside it, I'll show you some schematics of that. This has the A to D converter inside this one chip, right? To contrast that with the NI MyDAC, and I won't go through the schematic of this in great detail, but this, again, very similar. It has connections and so on. It has a USB interface, but again, this is designed as a data acquisition system, so you actually send it commands and tell it, hey, take some data, and then it'll send it back through the USB. It's not a program that's running continuously like on the Arduino, right? On the Arduino, you drop some code on there, and it starts grabbing data and possibly doing other things. Later on, we'll be asking it to maybe not only take data, but maybe do some control action based on that. With a system like this MyDAC, all you can ask it to do really is to grab data. You can have it send data out, but there's no onboard processing where it can run control code, for example, right? If you wanted to do control with the MyDAC, you'd actually have to do that on the computer and send that through USB. And it's possible to do some control, very slow, but it's not really designed for that, although we have done it in this lab for very slowly varying systems, right? A lot of measurement systems have A to D converters on them and look like data acquisition systems. Most digital multimeters have A to D converters, and kind of a segue to kind of show you a little bit about that. I know that you might have seen these before in the circuits class, but as you can see, even a simple digital multimeter schematic shows you that there is an analog to digital converter on here. There has to be all of this here represents sort of signal conditioning to get voltages in here so the A to D converter can actually process that and actually make sense of resistance measurements, right, or current measurements, right? You can't measure current with an A to D converter, but if you throw current through, across a resistor, for example, that resistor you can measure, right, the voltage drop, and you can infer current and so on. So A to D converters are the base of most things, and so kind of understanding a little bit about them can be helpful. Some of the key things about when you are specifying A to D conversion, which you'll be doing on the Arduino, is be mindful of resolution or the quantization, how many bits there are, because that tells you a little bit about how you can resolve voltages that you're measuring, and also the range, right? So resolution levels, and we'll talk about that, and the range. What are the maximum voltages that you can measure? Most of the time, A to D converters will be, low level. They're never going to have really high voltages. Usually, if you're measuring very high voltages, you would usually process that, protect the A to D converter from very high voltage, and then measure the lower versions of that through some signal conditioning. How fast you sample, right? So sample rates are important. And also, of course, how many times you're going to sample is important, because that has to do with how much of the signal you're trying to capture. For a particular platform, you need to think about how to configure the device, how to connect the signals is important, right? Which channels to sample, which pins in the case of an Arduino. Channels is usually a term that's used for data acquisition systems. Channel 1, channel 2. Whereas on the Arduino, we kind of think of the same thing, although we're thinking of more of the pin number is that we're connecting directly to, and then of course how to deal with the data, right? So A to D converters can convert analog voltage into some digital form, and there's always a full scale that you have to think about, and what is the full scale that's allowable. I'll show you the specs in a second for the Arduino, but first, like for an example here for the MyDAC, they tell you directly, on the analog inputs you can measure up to plus or minus 10 volts, or plus or minus 2 volts. You can actually switch that, and this is DC coupled. There's also an audio input where you can measure really high frequency, like sound, music, and so on, and that's plus or minus 2 volts also, but that's AC coupled. I won't go into that, but basically AC coupled signals basically have a capacitor in series. It takes out the DC part of a signal, right? So if you had a DC part of a signal, it would remove that and only look at the variation. So if you think of the sound of a signal that is only time varying part is important, you don't care about what we call the DC part, which is kind of like the constant part. So AC coupling will remove that. Usually that's really good for high frequency stuff. And when you're trying to measure stuff all the way down to really low frequencies, it's important to have DC coupling. Okay. Obviously, that kind of conditioning, that kind of circuitry is not available on something like an Arduino, because we're putting signals right into that A to D converter that's on the microcontroller. If you want to AC couple something, you have to build that circuit yourself, right? We won't revisit that later. You can look that up on your own. So one of the things you have to think about on the A to D converters is how many bits you have, and that's going to determine the quantization or the resolution, if you like. And you can figure that out easily. Usually it's just the full scale voltage divided by 2 to the number of bits, right? And for example, if I had a 10 volt range, I had an 8-bit converter, that I would be able to resolve voltages by 39 millivolts. And here's the little figure that kind of shows that, okay? I'll move past this, but you can see the difference. If I had a 3-bit converter, I'd have a terrible quantization problem, whereas if you have a 16-bit converter, you have a really nice resolution, whereas if you have a 3-bit converter, it's really, really rough, right? helpful to know the types of A to D converters, although most of the time you will likely run across, for example, the same type. And I've got listed here, there are some A to D converters that have simultaneous A to D. I remember I worked on one of those a long time ago, more high end. And what's happening is that you have separate A to D converters then, and it's really important that you measure all the signals at the same time. Maybe very high, scan rates are important, the sample rates. The most common is a successive approximation. There usually you have one A to D converter, and you might have a multiplexer so you can take multiple signals and you have usually a sample and hold, and then you can successively go through and approximate all the different. The successive approximation is how the approximation of the analog voltage is done, but what the multiplexer and the sample and hold help you do is switch between them. And usually you have to switch between them very quickly so that you can have higher sample rates, right? If your A to D converter has a sort of the highest sample rate it can accomplish, let's say you could do 100, to make it simple, 100 samples per second. If you had two channels, then it would cut it down to 50 samples per second, right? So the more channels you would have, you'd actually obviously cut down the sample rate you could have, right? And then these others are more common in, for example, in digital multimeters, slower conversion capabilities on these other types, right? So I just thought I'd show you a schematic from, if you go look it up in this electronics circuits book, you'll see that there's a register that does the successive approximation. There's actually a D to A converter that's used within an A to D converter. So it's got both of those types of circuits that help you approximate in digital form, right? The binary form of the analog voltage. So you can see there's a least significant bit all the way to the most significant bit, and so like this shows a what is it? It's a 3-bit converter, and the voltages that you can estimate, and the jumps between them, and what the binary is, and so on, right? So a nice little example just to show you what that schematic looks like. One of the reasons I wanted to show it was because I pulled out of the data sheet for the microcontroller that's on the Arduino, which is the ATMega 328, and you can see it's a successive approximation A to D converter. So here's your multiplexer, right? It's got the D to A converter, right? Sorry, this is wrong. This is digital to analog converter, not D to C converter, and then there's the conversion logic and so on. And then this is the bus where it communicates with the rest of the microcontroller that it's telling it, controlling the process and so on, right? So I wanted to show you that the A to D converter in the ATMega is a successive approximation, and most right here, right? It's a 10-bit, right? It's a 10-bit converter, which is important, right? So your resolution is going to be the full scale divided by 2 to the 10, right? And the full scale, what is that? Well, it tells you in the specifications, and I think I've got that on the next page. Here you go. The specifications here for the A to D conversion of the Arduino. It's got a 10-bit resolution. Here it tells you something about how fast it can convert, what the peak samples per second is that you can have, right? And by the way, again, the number of channels, I think that's going to knock it down based on the number of channels. If you're sampling, all the channels that you can sample, it's going to slow you down. There's 6 multiplexed single-ended input channels, and shortly I'll show you what that means. And then there's 2 more additional multiplex single-ended high channels that are not used for A to D conversion. So you only have 6 analog channels that you can sample. Oh, and in here I put it in red. The full scale voltage is going to be whatever the VCC is, and on the ATMega that's going to be 5 volts. So 5 volts is the highest that you can measure, that you should put into one of these pins. I don't know if there's an overload on here. Sometimes these guys, but I would be very careful and not try to overload that voltage very much. Divide that by 2 to the n, and it'll tell you what. Oh, I have it worked out right here, right? So 5 divided by 2 to 10, and you have about a 10 about a 10 millivolt resolution, right? So if you're trying to, so this is why you need to have big enough signals. If you're trying to resolve, sub 10 millivolt changes in a signal, you're not going to be able to tell the difference, right? So that's important. We may later look at an A to D converter. You can buy an A to D converter with higher resolution and communicate with that from an Arduino. And sometimes if you need higher resolution, that's possible, and you can find those types of A to D converters to use with Arduinos as well. Okay. Transitioning now to sampling of the signals and what's important in terms of the sample rates. Again, the A to D converter samples according to some scan or sample rate, right? Sometimes you see the notation the SPS or just samples per second. Sometimes, again, you might see that in hertz, right? So how many times per second are you sampling? How fast you sample, right, should be as small as possible so that you can reconstruct the signal. And people talk about the Nyquist criterion, which is, I need to sample at least 2 times the frequencies I want to resolve, but really you should try to go faster if you can. And sometimes the frequencies that are inside a signal, if you have noise and so on, you actually want to resolve those too, or you want to filter them out otherwise. So the whole reason for satisfying Nyquist is so that you don't alias, so you don't in reconstructing the signal, you don't create components in the reconstructed signal that look like other frequencies, and that's what aliasing is. And so sometimes what you might have is what's called an anti-aliasing filter, is basically like a low-pass filter. So let's say you only wanted to capture signals up to 10 hertz because everything's really low frequency. You might put a 15 hertz, or maybe even sometimes, let's say you want to go up to 10 hertz. I've heard some people rule of thumb, I'm going to put an 8 hertz low-pass filter on there. That way it cuts off everything, because low-pass filters roll off slowly, and that way it cuts off everything above 10 hertz, right? And all the noise is hopefully reduced, and then you can sample with Nyquist. I'm going to sample now twice the highest frequency, 2 times 10, and that way you can really, really not be worried about having aliased noise or other components that might be present in the signal, frequency components in the signal. There's other reasons that you might want to sample faster, and you might not want to sample real fast sometimes because you're grabbing a lot of data and you might not be able to store it all. So sometimes you have to worry. That's something you have to worry about with the Arduino, is if you sample too fast, you have to dump that data. So you have to make sure you have a fast enough baud rate so that you can grab that data. That means your computer has to have a good enough serial communication so that you can grab all the data that is thrown. So there's a lot of things to balance here, right? When you start thinking about starting to sample at higher rates and so on. Limitations of your device, the limitations of your communications and so on. And of course, how much you can store, right? All the data, if you're streaming it, you're gonna have to do something with it. And so if you sample at really high rates, you also have to, you're accumulating a lot of data. Nowadays, storage is not as big an issue, but if you have a little small mobile application, small robot, low memory, then you might worry about that, right? Again, one of the biggest things is looking at the frequency component, trying to sample fast enough to reconstruct it. So this just shows a few little examples here, right? Of hey, what have I sampled? This is 2 samples per cycle, and you could probably reconstruct the signal here. With this guy, you probably wouldn't be able to, right? You think about, if I put a sine wave through here, it would not look anything like the original signal. Whereas if I sample this signal at 16, I'm easily going to reconstruct that, right? So here's the minimal, right? You want to sample at least twice per cycle, right? And that's the minimum. Going to 16 per cycle allows you to really resolve that signal very nicely, right? Capture much more. We're not always fortunate enough to be only measuring nice harmonic signals this way. So you're going to think about the higher components too, right? Again, I like to put this slide in here, especially for this lab that we're going to be doing up close here, is we're trying to also, look at maybe measuring the period of oscillation. In that case, Nyquist doesn't necessarily help you. You want to worry about, hey, I want to be able to measure the period between, zero crossings or between, cross peaks. And so I need to have, enough data points so that the error in trying to estimate my period is small, right? Think about the delta T then is basically the resolution of how well I can predict, how well I can measure the period of oscillation, right? So trying to get a smaller delta T is important, like in the case of this pendulum oscillation, right? And that's a very simple example. So in that case, again, we're not worried. Nyquist is, we don't even think about that. We think about time resolution. Now moving on to making connections and grounds. Had a friend of mine a long time ago who was a double E teach me about, be careful, and we learn this now in circuits as MEs as well. Not all the grounds are the same the world round, and that's a saying that kind of an old school. And here you have 3 different kinds of grounds, and then there the names that are conventionally used. There's a chassis ground, there's an earth ground, and a circuit or signal common, right? They're all different types of quote grounds, and I like to put this here so you can connect them to one another, and I'm going to actually leave that open for you to go and find out more about these. The MyDeck has both what they call analog and digital grounds. The Arduino doesn't seem to distinguish. It has a ground. What type of ground is that? It's something for you to think about and be careful with, right? Is the ground on the Arduino the same as the ground on your the plug in your house? Is it the same as the ground on your computer? So these are some things that you have to be really careful about when you're connecting things. Okay. Making the right connections, again, sources can also be different, and sources can be sources of a signal. So it could be a sensor, right? And those grounds, are they grounded to, and this is a chassis ground, go back now and check that out. Are they grounded to earth or chassis, or are they or are they not grounded, right? This is a floating source, right? So some sensors are not grounded at all. So be careful there again, okay? Here's an example from the MyDeck. I've actually already moved into the appendix, so I'm not going to talk about this. I'm going to end this discussion, but you can see that they're very careful about having different kinds of connections on the MyDeck. On an Arduino, you're supposed to manage that, so you have to think a little bit more about it and be very careful how you connect things. On some more planned out data acquisition hardware, you actually also have the option in software to manage those connections. I'll stop the discussion here now.